Hi, everybody. I want to give a little shout out to our collaborators throughout the United States and Europe and Australia and South America. I'm going to talk about some lessons that I've personally learned through deploying our automated continuous monitoring system at hundreds of sites. So thanks a lot for hanging in there and listening. I'll talk about the background and provide some context. I'll describe the approaches that we take, some key questions that we try to resolve as quickly as possible. And then I'll point to a few projects and some of the lessons that we've learned, and then a few findings that I find exciting, and hopefully you will as well. And so as those of you that work in vapor intrusion arena, understand there are a lot of different things that can control the dynamics that we see. You've got soil contamination, you've got dissolved contaminants, you've got indoor products and outdoor air that might even contain some of the same compounds you're looking for. You've got sewer lines, maybe you have laterals that connect to sewers that might have some of these constituents as well. And then also when the vapors are going across the foundation, typically that's driven by differential pressure. It's an advective flux. And don't forget about what people are doing inside, HVAC systems, fans, wind, etc., weather. But the bottom line is that it's very complicated and the concentrations are changing continuously. And acknowledgement and recognition of that, in the US EPA 2015 Vapor Intrusion Guide, they point out what can cause dynamics, and then they encourage conservative assessment. And they also try to emphasize that every building's different. So this is language from that document that has served as sort of a Bible for a lot of us over the last decade or so. And then they also point to what they refer to as reasonable maximum exposure, and they encourage us to base key decisions about managing the vapor intrusion risk on this reasonable maximum exposure. More recently, and in the coming weeks, you'll probably see this or something similar. The ITRC draft vapor intrusion guidance also acknowledges dynamics, and they're encouraging a conservative type of assessment. And so their definition of reasonable maximum exposure is the highest exposure that's reasonably expected to occur at a site. And then they describe different ways to determine this or estimate this RME. A couple of takeaways from EPA's recent vapor intrusion workshops that have occurred in the West Coast and East Coast AEHS conferences include the fact that traditional methods can result in false negative decisions and poor characterization of long-term exposures, primarily because of the dynamics and how randomly timed samples aren't always able to coincide with when vapor intrusion is actually occurring. In fact, this is a quote from Henry Shuver: greater than 50% of the indoor air exposure occurs less than 10% of the time. That's pretty dramatic. They also conclude that 1 to 4 samples of Suma canister or rounds of Suma canister, 24-hour Suma canisters, are rarely ideal. And then they point to well-established tools that can improve this approach. And they not only discuss building pressure cycling and portable GC mass spec systems, but they also mention real-time on-site continuous gas chromatography systems. And I'll describe one of those. It's essential to know the causes of these dynamics, these controlling factors. Why is that? Well, based on the data that I've been seeing, this reasonable maximum exposure occurs when vapor intrusion is what people refer to as being on. And that's when vapors are actually flowing upwards advectively. And that's based on the differences in pressure between the subsurface and indoors. And that helps you prioritize buildings. If you've got multiple buildings you're looking at, you can distinguish between indoor sources and vapor intrusion. I'll show you that. And you can identify vapor entry pathways. I'll show you that as well. And you can evaluate risk, design and confirm mitigation, and ultimately move the project forward faster which reduces the exposures as well as the costs. And so there are a couple different technologies out there. The one that we prefer, at least for now, unless some of you out there can point me to something that that we should be considering, is the field deployment of a laboratory-grade gas chromatography system. It's fully quantitative. It allows us to take discrete samples with syringes. You get about 50 runs per day, or we can use this in a monitoring mode, continuous monitoring mode, where you get about 150 laboratory-grade analytical runs per day. We can reach ultra-low levels, regulatory levels for TCE, PCE, vinyl chloride, non-halogenated volatiles like petroleum constituents, methane tracers, etc. The analytical runs are typically less than 10 minutes per. We can cover a lot of space. We can accommodate for up to 16 points that are as far as 300 meters from the system. It's a modified EPA method TO14A, and it's very stable. If you look in the image to the left there, you can see sample inlets, and we have a valve that we've customized, and each of those pieces of wire there is actually a tube, and those connect to sampling tubes that we then deploy to locations that we have GPS coordinates for. And then all that data is pushed to the internet for real-time cloud-based assessment. And we combine that with weather data as well as differential pressure sensors. So this allows us to sort of put glasses on for the first time when we see the interplay of various data streams. We built our own system for tracking differential pressure and sending that back to our system or the web. If your eyes are good, on the lower right, you can see that we're connecting to a vapor pin. But this data is coupled to our concentration data and our weather data. And this tells us what direction vapors are flowing advectively. When the pressure is higher in the subsurface than indoors, the earth is exhaling. When the pressure is higher at the surface, like a Santa Ana condition, for those of you in Southern California, you know what I'm talking about, then vapors are actually flowing into the subsurface. The applications are numerous. We can do initial screening for large sites and small sites. We can rapidly answer some key questions that I'll spell out for us. We can determine building-specific attenuation factors. We can rapidly assess and even close sites with this kind of data. We can resolve mysteries. In fact, the vast majority of our hundreds of sites and projects that we've worked at are where previous assessments have been conducted, but they couldn't answer some of these key questions. And we can help optimize and confirm mitigation. We've worked on research and development projects. I'll describe one. And we also have worked on remediation projects where folks were concerned about emissions, like thermal projects, amendment projects, like those that we just heard about, where you might be concerned about methane or vinyl chloride, etc. So the key questions, and I like to ask our clients when they first approach us if any of these questions are on their list of what they'd like to resolve. First off, is there an exceedance indoors of the volatile organic constituents? If there's a concentration exceedance, then is it due to an indoor source, or is it really vapor intrusion? Interestingly enough, that seems to be what holds a lot of these projects up, particularly if you're in escrow. That's going to be a frustrating answer or a frustrating question. And if an indoor source exists, what is it? Where is it? If vapor intrusion is actually occurring, where are the vapor entry points? And if it's occurring, when is it occurring and for how long? That last question is really related more to risk assessment. And then the second set of questions is what can be done to immediately reduce that risk, and did that solution work? And what we're seeing is that the dynamic spatial temporal data patterns give us answers to these questions very quickly. And this is empirical evidence as opposed to inferential lines of evidence. And I love empirical, unequivocal evidence. If somebody tells me that they think there's an indoor source, where is it? What is it? I can tell them that, I can answer that. And so when you're using the continuous monitoring of multivariate types of data sets, chemistry, weather conditions, differential pressure. Within a few days, you see these patterns and you answer all those first questions. And sometimes we can do it in one day, but typically it takes a couple of days, 1 to 3 days or so. And while you're out there, and I like what Jake had mentioned, be flexible. What we like to tell our clients is not only be flexible, but try things while we're monitoring and test questions. And that allows you to actually select a remedy while you're still out there. That's really helpful. A lot of our clients have been pretty ecstatic about being able to do things like cover a drain and see that that was indeed what was causing the exceedance indoors. A couple of images. Here's a gentleman that's deploying some of the sample tubing and running that back to where our staging area is, where the gas chromatograph sits. You can see this was a short duration, so we just use masking tape, but we can use things that are more rigorous and secure as well. We've also done some work where we rapidly assessed entire neighborhoods. And how we would do that is we would combine discrete samples with the syringes. You can see the syringes in the lower left, those types of samples with continuous monitoring where we had more questions. So the consultant would run around and grab samples from different rooms, different buildings, clean outs, etc. I'd be in the back of in this case, it was an RV that was rented and we converted it to a mobile lab. And then they basically, based on those results and maybe some other questions they have, we would go to specific buildings, plug the landline, and then run lines into different rooms in those structures. And in some cases, we would be monitoring multiple buildings at the same time. You can see we've got some traffic protector deployed there on the right. And now I'll talk about a couple of quick examples and some of the lessons. And again, all these examples are where previous sampling with traditional approaches occurred, but some of the questions that they had weren't answered. And in all of these, within a single mobilization of a couple days, we were able to answer those questions. So this image is starting to gain a lot more attention. It's been in guidance documents and many other publications. But basically what we're looking at is blue is the concentration of TCE in a woman's restroom, and gray is the barometric pressure. And as you can see, when the barometric pressure dropped, the TCE in the restroom increased. And not only that, but I'm going to point this out at least now, and then I'll talk a little bit more about it later. The faster that the barometric pressure dropped, it looks like the higher that concentration was. I'll come back to that. And so what we did was we also started, after a couple of days of monitoring, deploying a differential pressure sensor. In this case, the differential pressure that's positive shows that the subsurface is higher concentration than the indoor pressure. And you see a beautiful temporal correlation between barometric pressure, differential pressure, and concentration. So the barometric pressure drop led to a differential pressure where the subsurface had a higher pressure than indoors. The earth basically exhaled and vapor intrusion turned on. And that's when I believe we should be observing something that estimates the reasonable maximum exposure. That flux direction, the orientation of that flow, if you will, is really important. And it also, it has huge implications with respect to sample timing if you want to be conservative. How else can we use that? Well, in this case, we were looking at a former dry cleaner, and we monitored for a few days, and we were looking at barometric pressure. They didn't allow us to drill into the slab, so we weren't looking at differential pressure. But they also had TCE, and the consultant was concerned because the values for TCE wasn't sure if those were degradation of the tetrachloroethylene. And so we started monitoring, and lo and behold, this inflection point here where the barometric pressure started to rise and vapor intrusion basically turned off. You saw the concentrations dropping of tetrachloroethylene. But TCE followed a different pattern. When the building was closed, it acted like a flux chamber until people opened up the business the next morning. In that case, we had more ventilation, and you saw a drop in the concentration. And so what was great about this is we were able to determine that tetrachloroethylene was from vapor intrusion. Trichloroethylene was from an indoor source, which they eventually identified based on the spatial pattern. So this is a really nice example of being able to answer that question that seems very elusive to a lot of folks out there. We can test solutions in real time. So you can modify HVAC, turn on fans, air filtration units, seal cracks, cover drains, optimize vapor recovery systems. And this can be done while we're still monitoring. So again, I want to encourage people, if you hire us, to go out there, to come out there and try a few things. This is a situation in the Northeast where it was a former defense contractor, and we were seeing trichloroethylene. It was jumping all over the place in this one room, but they had a couple of drains there. And so the consultant was very clever, and he covered the sumps there. And sure enough, as soon as he did that, the concentrations dropped out. And that was a nice outcome for him. And it was really simple. You know, they spent less than $200 for some metal rod and Visqueen and some sandbags. And so this doesn't take brain surgery, but it's really, really satisfying when you see that happen. Here's a situation where they had a building that had a very large footprint. And so there were concerns that a subslab depressurization system might not meet their objectives. And so what they did was we started monitoring to get a baseline. And then as soon as they turned on the mitigation system, we immediately saw a drop in concentration at these locations. So that became intuitively obvious to the most casual observer, to the client, to the regulator, that yes, the subslab depressurization system was properly designed and installed. Okay, I'm going to change directions quickly here. This was related to a research project that we completed. You know, EPA recommends basing vapor intrusion risk decisions on reasonable maximum exposure, right? Because they want to be conservative. The attenuation factor is used to make risk management decisions, right? So if the attenuation factor roughly equals the concentration in the indoor air divided by the concentration in the subslab, shouldn't the attenuation factor equal the reasonable maximum exposure divided by the subslab concentration? We'll see. Let's test that out. And there's a big debate now that folks are have been you know, entering and battling around for the last you know, 5 to 8 years or so. EPA in 2012 came out with their study that concluded that 0.03 was an appropriate default attenuation factor from soil vapor to indoor air. There have been many other studies since then, and they're all great studies, and they have various outcomes and various databases that they use. And the range is, the conclusion is the range looks like it goes from about 0.001 to about 0.1. However, all of the data used is randomly timed samples, right? All of the data are results from randomly timed samples. The reasonable maximum exposure when vapor intrusion is on and the distance from the sources were not considered. And I'll show you why this is important. So what attenuation factor do we observe with samples time to capture this RME, or this vapor intrusion on condition? So we went to 3 different buildings and tested this out. There's not enough time for me to cover all of this, but I'm going to talk about one of these. It's a warehouse study. So we looked at the subsurface and indoor concentration, differential pressure, and climatic parameters. And here is some of the data where you see time series for barometric pressure, differential pressure, the subsurface tetrachloroethylene, and the indoor air tetrachloroethylene. And you can see that I highlighted all the drops in barometric pressure, and each of these coincided with increases in differential pressure and increases in the indoor air concentration. That's when vapor intrusion essentially turned on. Okay, so what did we learn from this? It looks like the attenuation factor is dependent upon the timing, but also the distance from the source, okay? And so if you look at this ratio, if you're over the source, then you're going to have a higher subsurface concentration, so the attenuation factor is going to be lower. If you're farther from the source, then what's going to happen is you're going to have a higher attenuation factor, right? When vapor intrusion is on and you're farther from the source, there's a lower subsurface concentration and you have a higher attenuation factor because you also have a higher indoor air concentration. If vapor intrusion's off, you know, there's a higher pressure at the surface than in the subsurface, and the closer you are to the source, you know, right over that source where you have a higher subsurface concentration, you get a lower attenuation factor. The range that we saw was about 0.001 to as high as 0.4. So the spatial distribution of the subsurface plume relative to the sample pair location is going to dictate what you conclude with respect to the attenuation factor. This is extremely important. A couple of other things that we learned. I started to look at the rate of barometric pressure drop, and I noticed that for each episode, the higher that the drop rate, the faster that the barometric pressure dropped, the higher the concentration for that episode. That is a eureka moment because I can plot that, and every building that we've done this for has a different y equals mx plus b model, if you will, with very good R squared. That tells me that I can model the building. I can predict what the concentrations will be based on the barometric pressure drop rate. Okay, so I did that. My colleague, Ryan Solji at UC Santa Barbara, and I applied machine learning, and we looked at the NOAA record for barometric pressure because we've got a lot of that data. And we, using machine learning, applied that building specific model for the VI on conditions and plotted 1 year in the past, 2 years in the past, and 5 years in the past. And all of these points represent the predicted concentration given those barometric pressure drop rates. And so there's a lot of implications with respect to risk, reasonable maximum exposure, attenuation factors, mitigation design, but we can identify worst case causes. We can close the site quickly if you're never going to exceed a risk screening level. And what's really exciting to me is I can look at a weather forecast now and I can figure out what the threshold barometric pressure drop might be for that building, and I can warn occupants to stay home that day or do something to have higher air exchange. The other thing that we found is that the pressure drop rate, not surprisingly, also impacts attenuation factor estimates. And not only that, but the differential pressure. So they're all intertwined. So the drop rate impacts differential pressure, which impacts attenuation factor. So lessons learned. Differential pressure is key. I highly recommend measuring that whenever you can. And if you can't, try to get a good surrogate. The barometric pressure drop rate could help out. The dropping barometric pressure, the rising differential pressure goes to the vapor intrusion on. When these are correlated, you can predict the past and future exposures. Within a couple of days, we can build a building specific model. We just have to see a couple of barometric pressure cycles. The summer versus winter scheduling actually misses the point. It's not about the season, it's about the prevailing conditions. So you can go out there once, and if vapor intrusion's on while you're measuring that sample concentration, you can close that site, because if you have no exceedance during upward flux conditions, there's no risk. That's exciting to me. Again, the attenuation factor result depends on the distance from the source and the timing, and none of the publications to date address those two controlling factors. Some of the advantages of continuous spatial and temporal monitoring versus traditional methods: indoor versus subsurface sources, we can identify these in one visit. We can identify vapor entry points in one visit, identify controlling factors. We can evaluate vapor intrusion on versus off using differential pressure, so that can help you with attenuation factor and risk assessments. We can answer these questions while you're still deployed, and you can test potential remedies in real time while you're still deployed, and therefore you can move the project forward, reduce the risks, save money for your clients, reduce the liabilities. And that's what I have to share, and I hope you found this to be of interest.